Hey everyone, we're going to move on to the next part of our lesson on curve sketching. And we're going to talk about vertical and horizontal asymptotes. And we're going to show you that this is actually not a new skill for you. So when you pull up our lesson, you see everything that we have in here now is all about rational functions, right? It's numerator divided by denominator. And we have some dividing by zero situations kind of happening here. So when we look at our first example, 3x minus 2 over x minus 1, and if you graph it, you can actually already see what your answers are again. You've got a horizontal line happening here at y equals 3, and that's going to be our horizontal asymptote. And for the C part, where is your vertical asymptote? It's happening right here at x equals 1. So again, what we're really going to do then is we're just going to focus on what is the math behind justifying what you see in your graphs. So you know the horizontal asymptote is y equals 3. And if you go back to what we did earlier on in our course, we were talking about asymptotes. Lots of times we're talking about what happens as you approach infinity. So as you approach positive infinity or negative infinity, you see the blue lines approaching 3, the blue lines approaching 3. So what's the algebra that we have that goes with going to infinity? Well, that goes back to finding limits for your function as you approach infinity. And if you remember how we did that a couple of chapters ago, we wrote our function, it's approaching infinity. And we used a property that 1 over a big number or x over, not x, 1 over a big number, 2 over a big number, 3 over a big number. That's 0. And we want to try and figure out what is the constant value that we're approaching. So we look at our function. What's the largest degree? These are both degree 1s. So we just multiply by 1 over x in the expression. We multiply through. Now we have 2 over infinity and 1 over infinity. 2 over infinity is 0. 1 over infinity is 0. These constant terms, remember back to the idea of graphing a constant, y equals 3 is always 3, y equals 1 is always 1. So here's the algebra then that you use to justify y equals 3. It's about going to infinity. And again, if you think back to Math 20, how do you find vertical asymptotes? What causes your function to divide by 0? So x minus 1 is 0, x equals 1. So our graph then, y equals 3 and x equals 1, those are the equations for the asymptotes. And make sure when you're doing equations for the horizontal asymptote, make sure you always talk about y equals 3. If you just put a number, it's not an equation. The number's a number. It's not an equation. Same thing here. 1 is not the answer. X equals 1 is the answer. So that's a quick intro for example number 1. Example number 2, go to infinity. What causes dividing by 0? Question number 3, go to infinity. What causes dividing by 0? Question number 4, go to infinity. What causes dividing by 0? So again, you can see we're just working with largest degree was 1, so it's 1 over x. Largest degree was x squared, it's 1 over x squared. And here's x squared, so it's 1 over x squared. And then just some factoring skills. So really, when we talk about vertical and horizontal asymptotes, a little bit of algebra, but nothing too crazy. Let's spend a bit more time, though, on question number 5. And it's not about the A part of question number 5. It's about the B part of number 5. Can you cross your horizontal asymptote? Because lots of us think that's not possible. But anyways, here's your function, x squared minus 6x plus 8. Wrote it out nice with an equation editor this time. Multiply by 1 over x squared. Get my y value is 1. So down here, my y equals 1 is my asymptote. And what causes divided by 0? Again, little factoring skills going on. Factor out x. X equals 0. There is a vertical asymptote. X equals 1. There is a vertical asymptote. All right, so we've got things happening horizontally and vertically here. But you can see your function, the blue line, actually crosses your asymptote. It actually intersects your asymptote here. So a lot of us think that that's not possible. And my little note down here is just saying that really when you're talking about horizontal asymptotes, we're talking about what are you approaching as you approach infinity. So happening to cross here down here or somewhere around 1, that's not a big deal. We just want to make sure that as we get to infinity, we're approaching our constant term. So same thing over here on the left-hand side. We want to be able to approach a constant term. So how do you know if your asymptote's going to cross or not? Well, you can use algebra. So for our question, we know that y equals 1. That's the red line. And the blue line is x squared minus 6x plus 8 and x squared minus x. So if they meet, that's called an intersection. And what you learned back in Math 10 is if two graphs intersect, you can actually solve them algebraically. So your function f of x is 1. That's the y equals 1 part. And your function x squared minus 6x plus 8 over x squared minus x, you can just solve that equation. Right? It's a little cross multiplying, cancel out the x squareds, put the 6x with the minus x, and you get x equals 8/5. So the point then is the x value of 8/5 and the y value of 1. So that point right here where these two graphs intersect is 8/5 and 1. And similarly, you can use algebra to show that the graphs don't intersect, that the function doesn't actually cross its asymptote. So if you go back to the very first question we did, we knew y equals 3 was the asymptote, and our function is 3x minus 2 and x minus 1. Cross multiply, the 3x's cancel, and you add 3. Oh, it's probably not going to be 5. It's probably be something more like 1 there. Good mistake to make again. Doesn't have an impact on my solution, but whoops. 0 equals 5 has no solution. So if you can solve algebraically, that means your function crosses asymptote. If your function, you can't solve it algebraically, means your function doesn't cross the asymptote. All right, have some fun with asymptotes.